arguably the most important example is the following. Let V be the following set R times n times R. Okay, so we take the Cartesian product of R by itself n times. We will denote also in a more compact form this multiple Cartesian product as R to the nth power. Okay, so we would like to give two structures to V. Remember, one is an addition, the other is a multiplication by scalars, by elements of a field K, which is called a scalar field. So these two structures on V in order to make V a vector space. So we start with the definition of plus, which will make V an abelian group. So define V times V in V. So we define this function plus to be. Okay, so we have to take a pair of two elements, the first one in the first copy of the first factor of V, the second one in the second factor V also. So every element of V is an n-tuple of scalars, of numbers. Therefore we let the first n-tuple be a1 to an, and the second one b1 through bn. Okay, so the function plus will send this element to, so we have to give an element of V, so another n-tuple of numbers in R. Okay, so the n-tuple is defined to be the first coefficient of this n-tuple is going to be a1 plus b1, the second one a2 plus b2, and so on up to an plus bn. Okay, so now we would like to verify the properties that we listed in the previous talk. The first property, remember, is the associative property. Therefore we are going to pick three vectors in V, W and Z, and we want to check if the triple sum can be it doesn't change if we switch the position of the parentheses. Therefore, if we first take V plus W and then we sum the result with Z, so if this is the same as first summing V with the sum of W plus Z. Okay, now let's assume that V has coefficients Vi, W Wi, and Z Zi. So this equality this is actually an equality inside V. So inside Rn, the elements of Rn are n-tuples of numbers. Therefore, two n-tuples of numbers are equal if each coefficient of this n-tuple is equal index by index. Okay, therefore we can just concentrate one of the indices of this n-tuple and one of the indices of this n-tuple and see whether they are equal or not. So let's take the ith coefficient of these two n-tuples. So on the left hand side we will have vi. The ith coefficient of this n-tuple is going to be vi plus wi, and the result summed with zi. So we are going to ask whether this is going to be equal to the ith coefficient in this n-tuple, which is vi summed with wi plus zi. Okay, so this equality holds, of course, because these are just numbers, and associative property for the sum holds in numbers of R, in the elements of R, simply because R is a field. R is a field, so it has an addition operation, inner operation, and this addition inner operation satisfies the transitive property. Therefore, this implies the transitive property for all Rn. Okay, now property number 2 was the existence of the identity element. So we let the following element is 0 with the bar underneath. So this is going to be an n-tuple in Rn, which we define to be 0 in every coefficient. So 0 in the first coefficient, 0 in the second, so on, until 0 in the nth coefficient. So this is a perfectly legitimate element in Rn, where the 0, of course, is the identity element in R. So identity element for the sum structure, that is. So we end up having this n-tuple, and of course this n-tuple has the property of, and if we sum it with any other v, we will get the same result as summing it on the left or on the right, and this will be equal to just v. This is basically just by definition. 3 was the existence of an opposite element. So given v, we let minus v, the opposite of v, b. So we assume v to have coefficients v1, v2, v3. Okay, so in this case the opposite of v will be negative v1, negative v2, so on, negative vn. Okay, so we immediately verify so that v plus the opposite of v equals the opposite of v plus v equals 0. Okay, so once again the ith coefficient of this vector is vi plus the ith coefficient of the opposite of v, which is minus vi. Okay, so vi minus vi, this is an operation done inside R, yields 0, and this is true for every index I. Okay, now fourth operation is commutativity, which reduces to the following equality: v plus w is this equal to w plus v. Okay, so let's look at again at the ith coefficient of the left hand side and the ith coefficient of the right hand side. What will we get? We will get vi plus wi, and then on the right hand side we will get wi plus vi. But these are numbers, real numbers, therefore they are the same, they are just equal, and these for every I. Coefficient of this n-tuple and this n-tuple, therefore these two n-tuples are equal. This shows that V is an abelian group, an additive abelian group. Okay. In order to get something more, so to end of V of a structure of vector space, we'll have to define the multiplication of elements of V by elements of the field over which we want to construct the structure. Now, as we said, the only field we will be dealing with in this course is going to be R. Therefore, what we are interested in now is in defining a function that will go from R cross V to V. We will call this dot, and maybe with the V on the top to distinguish it from the product inside R, which will appear in the properties we will have to check. So we define this as, so we have to take a generic element in this set and say where we will be sending it to inside V. So an element in here is a pair of a scalar, a number in R, and an n-tuple inside V. Therefore, let me call the scalar alpha, and then the vector in V a1 dot an. Okay, so we'll be sending this element to the following n-tuple inside V, alpha times a1, so on, alpha times an, where the product here is inside R. Okay, so this is the operation dot V, and we have to check the four more properties, if you remember the previous talk. Okay, the fifth is associativity with respect of multiplication inside R. Okay, so we have to show that these two n-tuples are the same. The first one is alpha times beta times with this operation. So this is multiplication inside R, and this is multiplication as defined here. So times vector V is going to be just the same as alpha times in V with the structure V here, beta times little v. Okay, so to prove this equality, once again we will look at the ith coefficient of this n-tuple and the ith coefficient of this one, and we will show that they are the same. So here on the left we have, according to the definition, this explicit definition, we'll have alpha times beta times vi. Okay, and here on the right hand side of the equation, the ith coefficient will be alpha. So actually, more precisely, we'll have this, the product of alpha times beta, and the result being multiplied with vi. So here on the right hand side, on the other hand, we will have alpha multiplied on the right by beta times vi. So are these two numbers now? These are just numbers in R, so these are just real numbers. Are these two real numbers the same? Yes, because all these multiplications that we have here are all the same type, and it is the multiplication inside R as real numbers. Therefore, we have associative property inside R for the multiplication, and hence this equality holds. The next one is distributivity. So alpha plus beta. This is the distributivity law of times v dot v with respect of the sum in R. Is this equal to alpha dot v plus beta dot v? The answer is yes. Once again, we can proceed just as above, just concentrating on the ith coefficient of this n-tuple and the ith coefficient of this n-tuple. So this is true for every I, of course, and the same it will be here. So if you take the ith coefficient of this n-tuple, it's going to be the same as the ith coefficient this n-tuple, just because inside R the product here is distributive with respect of the sum, all inside R. Okay. The same goes for the seventh property, which is distribution law with respect of the sum inside V this time, not R but V. So alpha times V plus W, is this equal to alpha times little v plus alpha times W? The answer is yes, once again, exactly arguing just as in the step 6 and also as in the step 5. Last property, number 8, is it true that if you multiply on the left any element n-tuple in V by the element 1, the number 1 of the real number 1, we will get just again the same n-tuple? So is it true that 1 times V, it is going to be equal to V? Well, again, as before, the ith coefficient here is just Vi, and the ith coefficient here, by definition of this operation, is going to be 1 times Vi. But 1 is the identity element for the multiplication inside R, so leaves unchanged any other number when we multiply by it. Therefore, Vi multiplied by 1 is going to be Vi again, and this for every I. So this property holds as well. And this shows that V, which is Rn in this case, with operations, with operation plus and let's say dot V, is a vector space over R. Now, why is this vector space so important? Because we can actually see in special cases what the vectors look like, and these are strictly related to geometrical objects, and we will see in the next lectures that there is a very easy way to construct objects, geometrical objects associated to vectors in Rn. This is not the case for many other examples of vector spaces, which might be also very important, but we will not consider in these lectures.